This section covers the MIPS instruction set. I'm going to break down the instructions into two types. A machine instruction, which is directly defined in the MIPS architecture and has a one-to-one correspondence with a single instruction bit encoding. Most of these instructions are designed to execute in a single cycle as long as there are no data dependencies. Then there are macro instructions. These instructions are supplied by the assembler to make assembly coding easier. These instructions can be as simple as an alias to a machine instruction or translated into a series of machine instructions. While the macro instructions make it easier to write assembly programs, they will make it more confusing to debug an assembly program. This is because when the debugger disassembles a stream of instructions from memory, it will list them out as actual machine instructions and not translate them back into the macro instructions they came from. Here are some facts you should know before I begin telling you more about the instructions. For the MIPS 32 architecture, instructions have a fixed length of 32 bits and are always aligned in memory on a word boundary. In the MIPS architecture, there are 32 general-purpose registers, two of which are special. GPR0 always reads 0, which is useful when you are comparing a value to 0 because it's already in a register. And GPR31 is reserved for the return address from a jump and link instruction. All of the registers can be used for either address or data. Instructions can have 3 operands, 2 source registers, and 1 destination register. The immediate instructions have a 16-bit immediate value instead of one of the source registers. The assembly does allow for some instructions to be abbreviated to only have 2 operands, and I'll give you those examples when I get to those instructions. Arithmetic instructions can operate on whole registers only. There is no half-word or byte arithmetic. Some instructions have 32-bit and 64-bit versions. Double-length operands and results will go into high and low registers that are not part of the general-purpose registers. These registers are both 32 bits wide, and the high will hold the high-order bits, and the low will hold the low-order bits. Hardware floating point is an optional feature. This unit has its own registers, which are interlocked in the pipeline so that instructions depending on floating point results will stall and wait for the completion of the floating point operation. Floating point instructions are not covered in this section. For load and store instructions, there is only one addressing mode, and that is register plus signed immediate 16-bit offset. This offset, plus or minus 32K, covers a range of 64K addresses. All addresses are aligned to their data type boundary. Bytes and chars are 1 byte and aligned to a byte boundary. Half words or shorts are 2 bytes and aligned to a 2-byte boundary. Words, ints, or longs are 4 bytes and aligned to a 4-byte boundary. All offset values are in bytes. Load instructions will incur at least a 1-cycle delay even if it hits in the data cache. The core pipeline is interlocked on completion of the load data, which will cause the processor to stall an instruction if that instruction uses a register that the data is being loaded into. Compilers will try to avoid using data right after a load by trying to find a non-dependent instruction to execute after a load. All load instructions use a destination register and a source register with a signed immediate offset. Each type of load instruction has a signed and unsigned version. The signed version is sign extended, and the unsigned version, designated by a U, is 0 extended. The load byte instruction loads a byte from any address into the least significant byte of the destination register. The load half-word instruction loads a half-word from a half-word aligned address to the least significant bytes of the destination register. The load word instruction loads a word from a word-aligned address to the destination register. All store instructions use a source register and a destination register with assigned immediate offset. Store bytes store the least significant byte in the source register to any address. Store half word stores the two least significant bytes in the source register to a half word aligned address. Store word stores the contents of the source register to a word aligned address. Load link and store conditional instructions provide a very basic semaphore operation. For example, when a device driver is accessing part of shared memory that it shares with an interrupt routine. The load link store conditional instruction sequence provides a way to implement an atomic read modified write operation. You can have one active load link store conditional sequence active at a time. If another load link is executed between the load link store conditional pair, the store conditional from the original pair will fail. The read modified write sequence is completed by a subsequent store conditional which will either succeed in the store or fail depending on detection of conditions in between which may have caused the memory location to be altered. For a single processor system, any exception return or ERET in between the load link store conditional pair will cause the store conditional to fail. Here are some additional failure conditions that depend on the MIPS core being used. For a multi-threaded enable core, if any thread completes a store to the same cache line as the active load link store conditional sequence, or the thread executing the sequence is restarted, the store conditional will fail. In a multi-core system, using the MIPS Memory Coherence Manager hardware option, any processor that writes into the same cache line will cause the store conditional to fail. On an M4K implementation, the sync instruction is externalized to allow the ordering of memory writes by other memory elements in the system. If the sync signal is utilized like this in your system, then any write by any memory element to a 2K byte memory region that contains the word being written will cause the store conditional to fail. When a load link enters the instruction pipeline, it starts an active read modified write sequence, replacing any other sequence that was active. The load link bit in the CP0 register is set. Execution continues until a store conditional instruction is executed. If in between the load link and store conditional there is no exception or coherent store completed by another processor or coherent I/O module into the block of synchronizable physical memory containing the word, the store will succeed. A 1 indicating success is written to the source register. Otherwise, memory is not modified and a 0 indicating failure is written to the source register. Now I'll show you an example of a load link store conditional sequence. For this example, I will use general purpose registers T0 and T1. I could have used any available registers. The load link instruction will load the word into T1 from the address in the T0 register with a 16-bit immediate signed offset. The store conditional instruction will store the word in register T1 to the address in the T0 register with a 16-bit signed immediate offset. Here is an example of a binary semaphore. In this case, if the semaphore contains a 0, it is available. If not, it is in use and the code will need to try again. First, I load the address of the semaphore into the T0 register. Then I will load the value of the semaphore into the T1 register. I'll check the value of the semaphore to see if the semaphore is available. If it isn't, I'll branch back and try again. If it is, I will load a 1 into the T1 register and try to write it to the semaphore. I'll check to see if it was successful by checking T1 for 0. If it is 0, I'll branch back and try again. If it is non-zero, I have gotten the semaphore and I will continue to do whatever I need to do. Let's talk about unaligned loads and stores. Normal loads and stores in the MIPS architecture must be aligned. Half words may be loaded only from 2-byte boundaries and words only from 4-byte boundaries. A load instruction with an unaligned address will produce an address error exception, so you should install an exception handler. This exception handler could eliminate the desired load operation and hide the fact that the load was not aligned from the application. The exception handler could do this with a series of byte loads, shifts, and adds, but there is an easier and quicker way. Here is an example of an unaligned store with a combination of load word left and load word right instructions to get the job done with just 2 instructions. First, use the load word left to load the most significant 2 bytes of the unaligned address into the most significant bytes of the destination register. For this example, the unaligned word is in bytes 2, 3, 4, and 5. S1 is the destination register, and the register being loaded from is at address 0 with an offset of 2. To make it clear about what is happening before the load starts, S1 contains a hex 9, 8, 7, and 6. After the load word left, you can see that bytes 0 and 1 now contain C and D, which is the value in the most significant bytes of the unaligned address. Next, use the load word right to load the least significant 2 bytes of the unaligned address into the least significant bytes of the destination register. The least significant unaligned bytes are in the bytes 4 and 5. S1 is the destination register, and the address being loaded from is address 0 with an offset of 4. To make it clear about what is happening before the load starts, S1 contains a hex C and D, which we already moved there using the load word left instruction and a 7 and a 6 in the least significant bytes. After the load word left, you can see that bytes 2 and 3 now contain E and F, which was the value in the least significant bytes of the unaligned address. Here we see the syntax of the load word left and the load word right I have already shown you in the example. Here is the syntax of the store word right and store word left instruction that will store a word from a register to an unaligned address. The load upper immediate instruction loads the upper 16 bits of a register with an immediate value and zeros to the lower 16 bits of the same register. It is useful when you need to load a 32-bit immediate value into a register. The load upper immediate instruction loads the upper 16 bits with an immediate value, and you can use the OR-I instruction to load the lower 16 bits. The load upper immediate is used in the load immediate and the load address macros. The syntax is destination register, S1 in this case, and a 16-bit immediate value, X. Now I'll talk about the arithmetic instructions. The rule to remember is that all instructions use register length arithmetic. So in the case of MIPS core CPUs, that means 32-bit arithmetic. There is no byte or half-word arithmetic. Double-length results from a multiply and divide instructions are placed into 2 special registers called high and low. The least significant 4 bytes go into the low register, and the most significant 4 bytes go into the high register. There are additional instructions to move these values from these registers into the general purpose registers, which I'll cover later. Now I'll go over basic arithmetic instructions. Each one will have a signed and unsigned version. The unsigned version will end in U. First, the simple add instruction, which takes two registers and adds them together and places the results in a destination register. Next is an add immediate, which takes a 16-bit immediate value and adds it to the contents of a register and places the results in a destination register. The subtract instruction subtracts one register value from another and places the results in a destination register. As you can see here, there is no subtract immediate. You can do that using an add immediate instruction and just supply a negative number. The multiply instruction multiplies the value in two registers and places the results in the high and low registers. The divide instruction divides the value in the two registers and places the results in the high and low registers. One thing to note, what I am describing here are actual machine instructions. The assembler allows a broader range of these instructions through the use of instruction macros, which the assembler will interpret into actual machine instructions. For example, the assembler will take either registers or immediate values up to 32 bits and do the right thing. I'll cover more on this in the assembler section. Here are the set instructions. These will test two values and place a 1 in the destination register if the first register is less than the second. The other form of the instruction takes an immediate value instead of a second register, so if the value in the register is less than the immediate value, then the destination register is set to 1. These machine instructions are used by the assembler to create macros for branch greater than, branch less than, branch equal to, and all combinations of the three. There are two sets of instructions that will take the result of a multiply and either add or subtract it from the values already in the high and the low registers. As always, the most significant 32 bits are written to the high register and the least significant bits are written to the low register. These instructions will never cause an exception. In other words, the results can overflow without an overflow exception. The machine instruction syntax takes two registers and multiplies them together and either will add or subtract them from the high-low registers. Note, the assembler allows you to use immediate values instead of registers. Here is what I call a simple multiply instruction. It will multiply two registers and place the least significant 32 bits in a general purpose register. You need to ensure that overflows are either avoided or irrelevant because there is no overflow detection. Also, you cannot intersperse multiply instructions with the MADD instructions because the processor is allowed to use the high-low registers even though the results are stored in a general purpose register, so any accumulated results are not preserved across the execution of the multiply instruction. The machine instruction takes two registers, multiplies them together, and puts the results in a third register. The assembler will allow you to use immediate values in place of the input registers. There are two simple instructions to count either zeros or ones starting from the most significant bit. Count leading zeros starts at the most significant bit and travels backward, counting zeros until it finds a 1. Count leading ones does the opposite and starts at the most significant bit, travels backwards, and counts ones until it finds a 0. Now I'll cover the logical instructions. AND operation compares each bit of two input registers. If both bits are 1, then the corresponding bit in the destination register will be set to 1, otherwise it will be set to 0. OR operation compares each bit in two input registers. If both bits are 0, then the corresponding bit in the destination register will be set to 0, otherwise it will be set to 1. The NOR operation compares each bit of two input registers. If both bits are 0, then the corresponding bit in the destination bit will be set to 1, otherwise it will be set to 0. The XOR operation compares a bit in the two input registers. If one and only one bit is set 1, then the corresponding bit in the destination register will be set to 1, otherwise it will be set to 0. Now for the move instructions. There is a move macro which can be used to copy the contents of one register to another. This translates into an unsigned add of register 0 to a register to be copied and placing the result in the destination register, effectively making a copy. The next two are instructions that test a register for true or false, 1 or 0, and conditionally do a register copy. These instructions are normally used in conjunction with the set instructions to test their result. The last four move instructions either move from or to the high and low registers to a general purpose register. The shift instructions can be used to move bits around or used instead of a multiply if multiplying by a power of 2. They are also used to isolate particular bits before MIPS 32 release 2, but now we have the insert and extract instructions that do that much more efficiently. The left shift logical will shift the value in the source register to the left by the immediate value given, filling the bits with zeros. The shift left logical most notably looks the same as a no-op because a no-op instruction code is all zeros, and the instruction code for shift left logical is also zeros. So a shift left logical, where GPR 0 is both the source and destination register, and the shift amount is 0, interprets the same as a no-op. It also looks like a superscalar no-op when the immediate value is a 1 for much the same reason. The shift left variable is almost the same, but instead of an immediate value, you provide the variable value in a register. And of course, there are the equivalent shift right instructions. There are also the shift right arithmetic instructions that will preserve the signed value with the shift instead of just 0 filling. Branches change the instruction stream to a different path, usually based on a conditional evaluation. The processor needs one cycle to install the new program counter for a taken branch. So instead of letting this cycle go to waste, the processor will always execute the instruction that follows the branch. This is a good place to do a loop increment. The assembler will fill this branch delay slot with an instruction of its choice. If that is not what you want, you can use the set.noReorder directive to the assembler around the areas of code where you want to hand fill in these delay slots. If you do this, be careful not to place any branch, jump, error return, debug error return, or wait instruction in the delay slot. Branches have a maximum of 128K plus or minus displacement from the current PC location. The 16-bit immediate field is automatically shifted left by 2 bits to align it with a 4-byte instruction address, giving it a range of 18 signed bits. There is an exception to the rule that the branch always executes the instruction in the branch delay slot. In the case of the branch likely instruction, the instruction in the delay slot is only executed if the branch is taken and not if the branch condition falls through. The branch likely instruction is useful in loops where the code will loop several times through and the delay slot can be used to increment the counter. Most branch instructions have a likely equivalent and are distinguished by ending in an L. Here are the machine branch instructions. Branch equal will branch to the PC offset if the two source registers are equal. Branch not equal will branch to the PC offset if the two source registers are not equal. Branch less than 0 will branch to the PC offset if the source register is less than or equal to 0. Branch greater than 0 will branch to the PC offset if the source register is greater than or equal to 0. Branch less than 0 and link will branch to the PC offset and set the return address register to the next instruction after the delay slot if the source register is less than or equal to 0. Branch greater than 0 and link will branch to the PC offset and set the return address register to the next instruction after the delay slot if the source register is greater than or equal to 0. Here are the assembler branch macro instructions that fill in the other possible branch conditions. Remember, these are made up of one or usually more machine instructions. I won't go over each one of these now, but you could pause now and review them at your leisure. Let's talk about jump instructions. There are three types of jump instructions. Jump immediate will jump to an absolute address within the current 256 megabyte PC region. You supply the instruction with a 26-bit immediate value. This value is the target of the jump shifted to the right by 2. It is shifted to the right by 2 since all instructions are word aligned and the last 2 bits of the instruction address will always be 0. So the instruction uses this fact to pack 28 bits of address into 26 bits. The current 256 megabyte PC region is defined by the 4 most significant bits of the branch delay slot. So the jump address is the immediate value shifted to the left by 2, then concatenated with the upper 4 bits of the address of the branch delay slot. The good news is the assembler allows you to use the label of the jump target and does the shifting and concatenating for you. To reach outside the current 256 megabyte PC region, you will need to use the jump register instruction. The jump register instruction uses a register that contains a 32-bit absolute address, so the jump target can be anywhere in the 4 gigabyte address range. The jump and link instruction used to call a subroutine stores the return address into a register, R31, the return address register. Then, when the subroutine wants to return, it can execute a jump register with R31 to return to the caller routine. There is a delay slot for jumps just the same as there is for branches. To summarize the jump instructions, the jump instruction jumps to the address using an immediate value, the label supplied with the instruction. The jump and link instruction does the same as the jump instruction, and in addition it places the return address into the return address register. The jump register instruction jumps to the address in a source register, and the jump and link register does the same as the jump register instruction, and in addition places the return address in the return address register. Adding the .hb to the end of the instruction of the jump and link register will cause the CPU to stall and wait for all execution and instruction hazards created by any coprocessor zero state changes. I'll talk more about these when I talk about the EHB instruction. The system call instruction is used in an OS environment to transfer control from a user program to the OS running in kernel mode. The system call can supply a unique number, usually referred to as the system call number, which the OS can use to determine which OS function is being requested. The system call number can be retrieved by reading the instruction as data and extracting the code field. However, as we will see, the 032 standard uses an easier method to store and get the call number. Here is a run-through of using a system call in Linux that uses the O32 standard. The system call number is put into the V0 register. This makes it easier to retrieve instead of using the field in the instruction. The arguments to the system call are passed in the argument registers A0 through A3. Any return values can be passed back into the user code through registers V0 and V1. In keeping with the O32 standard, the OS, Linux in this case, must preserve registers as if a function call was being performed. The instruction is called with an immediate value, normally the system call number. Usually a user program is not concerned with the system call interface because it would use a standard library interface with the OS instead. Trap instructions are programmable conditional exceptions. Trap instructions evaluate a condition and cause an exception. For example, an OS can use them for assertions, which are usually conditions the OS assumes will never happen. Some forms of the trap instruction can have a 16-bit immediate value to pass information back to the OS. The OS might use this information to determine what happened. Since these are very similar to conditional branches, which I have already covered, I will not go into the details of each type of trap instruction. The break instruction is used by debuggers to cause a break in execution. As the user instructs the debugger to set a breakpoint, the debugger will replace the code at the breakpoint with a break instruction. Then, when the breakpoint happens, the exception will turn control over to the debugger. After the debugger has completed what the user wants, and the user has instructed it to continue execution, it will put the program code back and execute it. The break causes an unconditional exception. The core puts the address of the break instruction in the CP0 register EPC so a debugger will know where the break happened. The instruction can contain a 20-bit value that can be used to pass information to the exception. For example, the debugger could use this as an indication of what type of breakpoint it was, or a pointer to the program instruction that the breakpoint replaced. This information will need to be extracted from the break instruction word. The break instruction takes one immediate value. A new instruction introduced in MIPS 32 Release 2 is the bit extract instruction. This instruction can replace a series of instructions that would have previously been needed to extract a bit or bits from a word. For example, you would have previously needed to do a shift left and a shift right to extract a bit field to the least significant bits of a register. The extract instruction takes 4 arguments: the destination register, the source register, the least significant bit of the field to be extracted, and the number of bits to be extracted. For example, to extract 10 bits starting at bit 9 from register S1 to register S0, the assembly code would be EXT S0, S1, 9, and 10. This would start a copy from bit 9 of S1 to bit 0 of S0 for 10 bits. The remaining bits in the register S0 would be 0 filled. The counterpart of the extract instruction is the insert instruction. As with the extract instruction, this replaces several steps in merging a bit field into a word. The syntax for this instruction is the mnemonic INS. Then, the register to be merged, the source register that contains the bit field, the least significant bit in the destination register where the merge will start, and the number of bytes to copy. So a merge of 10 bits into register S0 from register S1 starting at bit 9 has the assembly code of INS, S0, S1, 9, and 10. This would start a copy from bit 0 of register S1 to bit 9 in register S0 for 10 bits. The remaining bits would be unchanged. There are two instructions that make interrupt control easier. First is the disable interrupt instruction. This instruction helps by atomically writing the value of the status register to a general purpose register and then clearing the interrupt enable bit in the CP0 status register. Enable interrupt instruction writes the value of the status register to a general purpose register and then sets the interrupt enable bit in the status register. Note, you might not always want to use the enable interrupt instruction, particularly if you're nesting interrupts. You might just want to restore the status register with the value it had when it entered your interrupt function, so it would continue with the processing of any interrupt function that you may have interrupted. The assembler syntax for this instruction is destination register where the status register will be saved. There is a software breakpoint instruction which works very much like the break instruction, except it causes a debug mode exception, which is tied into the EJTAG controller. A hardware EJTAG probe could use this instruction to set a breakpoint. Two instructions that can be used to return from exception handling. The exception return instruction will atomically clear the exception bit EXL in the status register and then jump to the address stored in the error program counter. The debug exception return instruction returns from an EJTAG debug exception and then jumps to the address stored in the debug error program counter. The syntax for both is just the instruction mnemonic. There is a special case where the error return instruction will use the error program counter instead of the error program counter. The error level bit is set in the status register during a reset, soft reset, non-maskable interrupt, or a cache error exception. Exceptions can happen while processing these exceptions, which are usually not recoverable, so using the error program counter is a way of not going into an infinite exception processing loop. The MIPS architecture does not allow arithmetic operations to be performed on anything other than integers. If there is a value that is less than an integer that needs to be used in an arithmetic operation, it must first be made to look like an integer. This can be done by sign extending a byte or half word. The sign extend byte instruction will propagate bit 7 from bit 8 through bit 31. The sign extend half word instruction will propagate bit 15 from bit 16 through 31. You can use the sign extend half word instruction in conjunction with the shift right arithmetic to sign extend two contiguous half words. First, you load two contiguous half words into memory. Next, you use the sign extend half word instruction to sign extend the least significant half word and copy the result into another register. Then you can use the shift right arithmetic with a value of 16 to shift the original value 16 bits and then sign extend it. There are three instructions that are used to manipulate bits within words. These instructions can be combined to swap the Indianness of a word with just two instructions. The word swap within half word instruction rotates bytes within both half words. Rotate word right rotates bits in a word for a given number of bits set by an immediate value. Rotate word right variable is similar but uses the value in a register instead of an immediate value to determine the amount of bits to rotate. Let's look at an example of an Indianness swap. First, load the word into a register. Next, swap the bytes in each half word using the word swap half word instruction. Then use the rotate word instruction giving it an immediate value of 16 to swap the half words. There are three instructions that are used in working with coprocessor 0. The move from coprocessor 0 moves from a coprocessor 0 register designated by a register and select number to a general purpose register. The move to coprocessor 0 moves a value in a general purpose register to a coprocessor 0 register designated by its register and select number. The EHB instruction will clear execution hazard barriers. Hazards are created when a move to coprocessor 0 instruction is used because there is no guarantee on how long it might take for the value to be written to be usable by another instruction. When the core executes an EHB, it will guarantee the value is safe to use by waiting for the value to be committed to the register. You should consult your core software user's manual for which actions cause hazards and how long the hazard will last. Depending on the action, not all move coprocessor 0 instructions will cause hazards, and for others, as long as the value that was moved will not be used in a set period of time, an EHB may not be needed. The read hardware register instruction allows access to some of the CP0 registers while in user mode. Permission to do this is set in the hardware NA register that needs to be set up while the CPU is in kernel mode. The assembler syntax for this instruction is destination register and operation code. I'll use this instruction in an upcoming example to get the sync step count, or opcode 1. The sync instruction will stall the system until all loads and stores are coherent throughout the system. The use of the sync instruction is only necessary when memory is being shared between two or more devices within the system. For example, if you are using a DMA controller to send data out of your system, you need to make sure that all stores to uncached shared memory area between the CPU and the DMA controller have completed before you start the DMA. In a multi-CPU system, you may need to make sure before you load a value from a shared memory region into a CPU that another CPU doesn't have a newer value that has not yet been written to the shared memory area. For example, it may have this cached. The sync only reflects uncached or cache coherent loads and stores. Cached loads and stores to non-shared memory are non-coherent, and you don't have to use the sync instruction for these areas. A sync is needed when changing the operating mode between normal and EJTAG debug and vice versa to guarantee changes made to memory before and after the mode change is visible to both the EJTAG controller and the CPU. The sync instruction will stall the CPU until all uncached and cached coherent loads, stores, and refills are completed and all interim write buffers are empty. The sync instruction does require external hardware to be able to propagate the sync signal to the external bus. The externalized sync bit in the config7 register of coprocessor 0 controls whether or not the sync signal is sent out to the external interface. The exception to this is our 4KE, 4KSD, and M4K cores, where the signal is always sent. The assembler syntax for sync is simply sync. The sync-I instruction is used to synchronize the data cache with an instruction cache. This is necessary when a program loads another program into memory because the load instruction only loads the data cache, and to execute the code, the instruction cache for that data region needs to be invalidated, so that when a fetch happens, you will get an instruction cache miss and fetch new instructions. the sync I instruction only affects the cache line of the address you give it. So, you will need to loop through all affected cache lines. You pass the address to the sync I instruction using a register with an immediate offset. Here is an example of an assembly function that can be used after code has been written into memory to synchronize the caches. The function takes two inputs, the starting address in register A0 and the size of the area to be synced in bytes in register A1. First, calculate the end address. Now get the size of the cache line. If the size was 0, we have no caches, so there's no need to do the sync I, so the code will jump to the return. Sync the first address. Check to see if it is the last cache line to sync. Use the delay slot to increment the byte count by the step size, and loop back if there is more to do. Once we have looped through all cache lines, use the sync instruction to sync any coherent memory so other devices that might be sharing the memory will see the change. And return, making sure that any instruction hazards have been cleared. Note, the jr.hb instruction could be replaced with a jlr.hb, an ERET, or a DERET instructions as appropriate. There are 4 instructions that control the translation look-aside buffer. These will be covered in detail in a separate TLB section. Likewise, there are 2 instructions that control the cache. These will be covered in detail in a separate section on the cache. The wait instructions can be used to control the power consumption of the CPU when there is nothing to do but wait for an interrupt. This instruction will be covered in detail in a separate section on power. There are 2 instructions that control reading and writing of shadow register sets. Since these work with interrupts, they are covered in detail in a separate section for exceptions and interrupts. This ends the instruction overview section. The next section on MIPS assembly will cover specific issues dealing with the assembler. Thanks for watching.